Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it's my great pleasure to introduce Eric Koskinen, who I'm sure is known to pretty much everyone in the room because he did his PhD in Cambridge and was working heavily with Byron, so was in the old building a lot. He's now at NYU in New York and is going to tell us wonderful stuff about local temporal reasoning. And he said it's only a 45-minute talk, so we can ask tons of questions. So get ready, Simon.
Thanks, Matthew. It's always a pleasure to give talks for you guys. So this work that we've been doing recently is on techniques for verifying temporal properties of higher order programs. And just to immediately set the stage as an example, here's a simple program in ML style syntax. It has a couple of recursive procedures. There's this first procedure called halt, which takes a single argument and then calls itself. It's kind of a funny name because even though it's called halt, it just continues to call itself forever and it doesn't halt. And then there's a recursive procedure called shrink, which takes a single argument, f, and what it does is it applies f to unit, and if it gets back 0, then it calls halt. Alternatively, what it does is it calls itself with a new partially defined function argument, which is a lambda expression that takes the result of applying f to unit and subtracts 1 from that. Then finally, there's the main procedure, which binds t to a non-deterministic but positive integer. That's what star plus means. And then calls shrink with a lambda expression that returns the value of t. OK, so a fairly simple program. Now, let's say you're interested in proving this temporal property here, main x shrink until halt. So if you've seen any temporal operators before, then some of that should be familiar. The x part means that first the left thing happens, and then the next thing that happens is the right thing. And then for the u...
What does it mean to say main happens?
I'll tell you in a moment.
Okay.
And then what the u, just as a refresher, what that means is that its left thing happens repeatedly until its right things happen, and moreover, its right thing must happen at some point. Now, it may be a little bit of a, if you've seen temporal logic before, the atomic propositions might seem a little different here. You might be used to sort of predicates or something along those lines. In verifying higher order temporal properties of higher order programs, the atomic propositions are typically chosen to be events. So we define an alphabet of events. I'll go through it formally in a moment. But for practical purposes, for most examples that we'll look at here, and also in practice, it's convenient to create an event for every procedure. And think of it as the moment that the procedure is called, it generates that event, that corresponding event. So what I'll kind of do is add a little bit of syntax here that says the event, the argument is generated. So for example, the moment halt is invoked, it generates the halt event. And the moment that shrink is invoked, it generates the shrink event. And similar for main. So now that we have this notion of events, we can think again of this.
Oh, wait, we don't quite have it. So if the thing's code, would it be, are you assuming that your functions here or procedures are uncoded?
Are what?
Code. So if halt took 2 arguments.
Right. Well, halts
then
took
a
a single argument.
You know, it would have the kind unit to something. So I guess the question is, how many arguments do you have to give it before the event happens?
Oh, it has to be a full application before the event happens.
So it's called by value.
It's, yes.
Yeah, but even called by value.
Yes,
it's
it's code functions. Yes. It's full of choice as to where you put.
So okay, so to a
there is a choice here, yeah.
Okay.
Okay.
And are you assuming a fixed order of evaluation?
Yes.
So
I'm
say
assuming a strict
E2,
evaluation.
It's all specified that E1 happens first. Otherwise, this wouldn't make.
That's
sense.
right. Yeah.
Okay.
Yep.
But in this model, nothing happens between events. Implicit.
I will get back to that in a moment. Thank you. That's good. Okay, so that's our notion of events. And now we might wonder, okay, well, does this property hold this program? Well, we can think about it sort of intuitively by starting to consider the different traces of this program. So one, for example, is where, let's say that t is initially bound to the value 2. And so in that trace, what will happen is the main event will occur, and then the shrink event will occur where f is a function that returns 2, and then shrink will call itself with a function that effectively returns 1. Now will sort of continue to recur until shrink calls itself with what is effectively a function returning 0, and then it will call halt. And if we look at this trace, you can say that that satisfies main x shrink until halt, because there's some first main happens, and then some finite occurrences of shrink will happen before a halt event. Yes?
Why do you have halt coded like this? Why not just halt stop?
So you could also do it, just have it be stop. Yeah,
Okay,
that's fine.
Nothing to do with halt repeating.
There's no reason why I had to do it this way. I just chose to. Yeah. Okay, so another trace is this one, where obviously t can be bound to something other than 2. Let's say 1, right? So I think we're all getting the picture here that if you consider any trace, that it's going to satisfy this temporal property, main x shrink until halt. Okay, so if we want to come up with a technique for being able to prove that this property holds the program, there's a number of challenges we have to address. So first of all, there's issues like non-determinism, there's issues like reachability, termination is involved in the strong until operator. There is an infinite state space here, dealing with integers and functions. And of course, there are higher order features. So given all of that, there are no existing techniques that are able to prove that this property holds the program. There have been a number of works in this direction, so I just want to highlight a couple of them. For example, the work of Kobayashi and Ong in LICS 2009 was able to prove very expressive logics, mu calculus properties, but they were restricted to finite data. Some have worked on higher order programs, but only safety or termination aspects of them. And then some work that Byron and I did in the past is able to prove temporal properties, but for first order programs.
So what do you mean by finite data?
So yeah, no integers, no data structures, obviously, and
Bit vectors.
what?
Just bit vectors.
Yeah, basically, I think, yeah.
So surely ML has a semantics. You could calculate that this property holds.
Sorry?
The program has a semantics, right? You could prove semantically that this property holds.
So one thing you could do is effectively take the program and treat it as a transition system. Is that what you mean? And give it a semantics, and then sort of compare the transition system to the temporal property and see whether it holds. Is that what you're proposing? Yeah, that is an approach, and actually what we've chosen is to do something that is intentionally different from that strategy, and I can come back to why that is. Okay, so well, what's the key issue here? Well, if we have something like a function application, like here when we're applying shrink to lambda.t, and we want to check whether or know whether shrink strong until halt happens. The problem is there's a couple things that might happen. When we look at the reduction of E1, we don't know if it's going to terminate or diverge. Same thing for the reduction of E2. And then, of course, there's also what happens when you apply the reduced E1 to the reduced E2.
So
again, we don't know.
Diverged in a value language, then the whole thing would immediately diverge. Does that
Yes.
satisfy shrink until halt?
If which diverges.
If either of them diverges, then immediately that term will diverge.
It depends on what
Without
events
any
are
shrinks or any
generated.
halts, right?
Yeah, but it depends on what events are generated. It's okay for the program to diverge. As it diverges, however, so as I'll show in a moment, it's impossible for the program to diverge without generating events, which goes back to, I think it was your question. But I'll come to this in a moment.
Oh, I see. So if E2, if evaluating E2 itself generated some events, then it wouldn't satisfy this property. In other words, the property would say exactly all of the things that occur. Nothing else can occur.
Yes.
If evaluating E1 took a whole lot of work, we finally got the shrink function. That wouldn't be good enough to satisfy this property. Is that right?
I'm not quite sure what you're saying. You're saying that if evaluating E1 did a whole bunch of things but didn't and diverged and never.
E1 was ID applied to shrink.
Okay.
Where ID is the identity function.
Uh-huh.
Then the event sequence you get would be something like ID followed by shrink.
Right. That's right.
And
yeah.
you're saying that would not satisfy this property.
No, you probably would need a slightly weaker property that said, like, ID happens and then.
Simply pipeline the calculus?
I'm not sure.
Well, you have anonymous lambdas and they don't generate events, so delta would diverge.
I promise I'm going to come back to that point when I show you the semantics.
So you're not able to hide events. I mean, there's a sort of.
That's right.
Yeah.
You can't hide events. Yeah.
This is pretty fine-grained.
Yeah.
You've got to be quite tricky to write down the property that you want. You can't say something like, this program never, keeps this valve open until it shuts that one.
You can.
Why not?
You could write other properties other than that, right? You've got other temporal operators.
Yeah, I just am choosing to do this.
Indeed, but you'd have to. There's all these other events might get in the way.
Right. So and I am going to come back to this, but there are other events will happen, and so I think part of this area of research is to understand how you can come up with specification languages that take that into account. And match what your intention is and sort of boil it down to something that accounts for all these other events that might get generated. Okay. So the issue here is, go back a slide. Right, again, we don't know whether or not E1 or E2 are going to terminate, diverge, and moreover, the application of E1 to E2, whether it's going to terminate or diverge. And so the way that we address this problem has kind of two decompositions to it. And the first one is super obvious and should be no surprise to anyone here, is to divide up the program into expressions. Right, this is the standard type systems approach. And think of this in terms of three separate specifications. First, phi1, which talks about the temporal behavior as E1 is reduced. And then phi2 that talks about the temporal behavior as E2 is reduced. And then phi3 that talks about the latent behavior when E1 is applied to E2. And given those specifications, we can say that the overall behavior is going to be some kind of composition of those three specifications. Again, really taking into account here that there's a particular evaluation order. Okay, so that was sort of the first part. Now, and then once we do that, we can kind of fairly straightforwardly create a type and effect system where we'll say that, for example, for a function application, it'll have some type. We found it useful to work with dependent refinement types and a temporal effect on the right-hand side of the ampersand. Now, the other thing we found was that in order to get things to work, we had to separately track the behavior of the finite traces of an expression from the infinite traces of that expression. So what we had to do is, rather than having these specifications, phi1, phi2, phi3, we had to split them into pairs. So we separately talk about what are the finite traces of E1, call that phi1 fin, and the infinite traces of E1, call that phi1 inf. So then we end up with all these different cases, right? There's the finite traces and the infinite traces of E1, the finite and the infinite of E2, and the finite or the infinite behaviors that occur when you apply the reduced E1 to E2.
So this is so you have more precision when you deal with until and stuff like that. Why do you have to split it? And you said to make things work, but what do you mean?
So that you could. So yeah, I guess the answer would be precision. So that otherwise you may have to end up like over approximating, and you kind of lose a bit of the behaviors. But once you break it down into these different categories, then we can come up with sort of compositions that consider all of these different cases. And I'll come back to that in a moment. But so the syntax we'll use here is now a type and effect system where on the right-hand side of the ampersand, we have two components. First, the finite specification, the finite component, and then the infinite component on the right-hand side. So in the subsequent slides, I'll kind of have this finite, infinite sort of arrangement to keep in mind. So now going back to this example, here, ultimately, we want to prove main x shrink until halt, which is not a super straightforward temporal property. But actually what our type and effect system will allow you to do is to break this proof apart and first have a part of the proof that's concerned with only the safety component or the safety aspects of shrink until halt. That is, what is the latent behavior that occurs when shrink is applied? Whenever we take shrink and apply it to a function, what happens? And our type and effect system will allow us to write down judgments of this form that say that, well, shrink, when it's applied to a function, is going to have this behavior shrink weak until halt. So weak until halt is like U, except that it has no guarantee that halt will eventually occur. So it's perfectly acceptable with weak until halt for shrink to happen infinitely and never to get to that second argument. So this is really kind of more just about the safety aspects of shrink until halt. Like what kind of events can be generated?
But you're assuming no effects on the argument, right? No latent effect on the argument.
Yeah, so I'm abbreviating a bit here with some of that, yes. So,
wait, so is it not true that shrink also has the type shrink U halt?
It is true, right.
So why did you say W here?
Because it actually, and in the derivation I'm going to show in a moment, it's convenient to separate out sort of the safety-ish parts of it from the liveness parts of it. So we could separately, for example, have a liveness judgment here that says that, well, if you have a function that returns an integer that is greater than 0, then shrink applied to f is going to have this behavior. For the infinite traces, for the finite traces, I'll just say top because in this judgment we don't know anything about what the finite traces do. But for the infinite traces, we'll say that eventually it's going to not call shrink or not generate the shrink event. It's going to generate something other than a shrink event. And this is kind of a termination or a liveness thing. We've really sort of boiled away a lot of the other temporal aspects of it into a judgment that's just about termination. So now what we can do is take these two judgments, the one that has these safety bits to it, and the other part that has the termination business to it, and in the type system combine them together to obtain the overall temporal property that we're interested in proving, which is the strong until property.
So if shrink took as its argument and another function, maybe it took halt as its argument. And here, the reason you can say eventually not shrink is because you know you're going to call halt eventually, right?
Yes.
Intuitively.
Yeah.
Right? Supposing you eventually don't call halt, but you eventually call one of your other arguments,
Mm-hmm.
which might, of course, turn out to be shrink.
Right.
Then in order to get this kind of property, you'd have to have in your assumptions about your argument something about what type would you get, maybe I should ask, for this liveness thing.
For the second judgment on the liveness?
Yeah. If shrink took another argument, which was the
which could generate.
But then since shrink, when you look at shrink all by itself, you can't see that. The argument, you don't know whether that second argument is going to turn out to be shrink itself or something else. So
That's
it's
right.
hard to get a property like this.
That's right.
So,
but
what will happen?
Isn't there an effect on the unit refinement type array in that case?
Yes.
Yeah.
One function can satisfy lots and lots of types, which are not comparable.
Yes. Yeah.
So you might have to conjoin them, right? It would have this and another type where this thing had an effect, and then something different would happen.
Andre?
So somehow I have a feeling that sort of in the beginning you build this big strum and saying that, oh, no one can deal with LTL, but okay, some people can deal with safety, some people can deal with termination, even for these higher order programs and for infinite data. And okay, that's all fine, but actually now, and then you said, okay, so I have this LTL property, I have a Bücher automaton, but I'm not going to actually compose the basically the complement Bücher automaton and go for fair termination. Probably that would be too simple. There are some reasons, not compositional. And I'm not going to use the type and effect system. Just say, okay, it's fair termination. Probably introduce a flag and reduce to this previous Terauchi's paper. But now it looks like still. So you are essentially saying, okay, this is one part that is essentially safety, and this is another part that's probably going to boil down to fair termination. So what's the reason?
So the reason is, and I think my next slide will sort of give you the answer. The goal that we were trying to do here is to be able to come up with a technique that was composable, so that you could have separate, in different parts of the type system, you can work on different aspects of it, and then combine this information together. So,
very vague.
Sorry?
This is very vague, but very useful. It's always useful to be a composition.
Right. Yeah. So the thing with the sort of fair termination approach, and there's still a question as to whether that ultimately is better in practice. I'm not convinced. But you do have to do some sort of global reasoning about the entire transition system. You have to take the whole thing and the negated automaton and do kind of global reasoning. And in fact, I think you also, with that strategy, you'd have to convert your program into CPS form first as well. And I guess personally, it's my belief that ultimately is not going to lead to tools that will be as effective as to be able to sort of separately talk about different things. You have like your termination tool that is able to prove that all these different loops terminate, and then you can just use that kind of once and do that once, and then separately do like sort of safety proofs that are more about taking like fixed points and so forth, and then kind of combine them. Whereas the other way, you have to, every time you make a change to the program, or you have to do some sort of global reasoning. So I'm going to wave my hands and say things about compositional reasoning as the motivation there.
Fair enough. Cool. Thank you.
Okay. So one thing that, as we were putting this together, was a little bit surprising is that there's like these liveness properties that show up in the type system. And I guess I always had this sort of feeling that you couldn't put liveness in the type system. But it seems like people are now realizing that's perfectly fine.
All the basic classical type systems are liveness, right?
All the
things terminate. Simple types, polymorphic types, systematic. They all show things terminate. They're all doing liveness.
That's true. Okay, so there's sort of a kind of trivial type of liveness, which is to say that they terminate, they reduce to a value. But what you can do here is you can carry around even more elaborate temporal specifications that have like real rich liveness properties. And it's okay for that. The type system itself can't, on its own, generate non-trivial liveness information. At least I don't know of any technique that's able to do that so far. But what it can do is carry it around, and in the sort of in the effect, and then combine it with other information. Like here, for example, when you have some liveness information about the termination of a particular loop or an eventuality, and then combine it with safety information. So this is kind of a way of taking oracles and combining them together. So what I haven't mentioned really so far is where do these pieces come from, the safety component and the liveness component. So the safety, a lot of times you can get it directly from the type system. It effectively arises as a fixed point solution to the typing context in the judgments over the body of shrink. So let's do the shrink example. So first, let's assume we've already typed halt, and we know that halt, when you call it, so it has this latent effect that it's just going to generate the halt event repeatedly. Then if we look at the body of shrink, and it has this if-else branch, right, we know that shrink is going to generate the event shrink, and then either a halt event is going to occur next, or a shrink event is going to occur next. And given that fact, we could think of one valid typing, which is to say either shrink or halt is going to occur. But we could come up with something, we could look for a fixed point, in fact, to this equation, which says that alpha equals shrink, and in the next step, either alpha or g halt. And when we look at it for a fixed point to that, one of them would be shrink weak until g halt. So these kinds of judgments can come from the type system itself. So then there's the liveness piece. Well, for the liveness piece, what we can do is, well, in this case, we kind of wanted to know what were the conditions under which shrink terminates. And I showed that a moment ago. And actually, we can, if we look at this example, we know that, well, the conditions are f has to be a function that will, it ultimately is going to halt when f returns 0. So the conditions has to be that f is a function that returns something above 0, because each time it calls itself, it'll create a new function that returns 1 less than the previous time. So we can get a judgment like this using some prior work on higher order termination. So we can kind of use those termination provers, some higher order termination provers, as one of the sort of building blocks or one of the sources of information into the type system. Of course, that's a separate proof, right? That's a whole separate iterative process. So in our type system, we'll have an oracle rule which lets you take that information from the outside and bake it into the type system with obviously some important conditions. Okay, so overall then you can take these safety components from a type system and liveness components from oracles and combine them together into the overall property that you're trying to prove. Yeah?
Can you go back one slide? So in particular, this mechanism using the external oracles, you end up not doing things like, okay, I mean, you have a recursive definition of halt there. And when you want to, say, infer or have typing judgments about liveness, you're not going to make hypotheses about the recursive calls that have liveness in them and then make inductive arguments that then show other things.
Yeah.
So you just don't have, I mean, that's the part of the type system that doesn't get along with liveness.
That's right. That's absolutely right. Yeah. Yep. And that's why I think it was important for us to sort of separate out the safety and liveness, because we don't want the type system to try and do that.
Yeah. And these oracles, they're not doing global reasoning, so to speak? I mean, have you shut stuff?
No, they don't have to. So in this case, what we can do is do some reasoning on just the shrink function, for example, without taking the entire function and or the entire program. And that's why it's really useful to use a dependent type system, because you can say, under these conditions, if I examine this procedure in isolation, on this kind of input, I can say that it terminates.
But shrink in isolation includes the definition of halt, right? I mean,
yes, so it's not completely in isolation. That's right, yeah. Okay. So I've kind of been through, sort of mentioned all these things. What we tried to do here is design a type and effect system that you could instantiate to a wide variety of specification logics. So the only real restrictions, I've used LTL as an example. Really, I've been using it as an abbreviation for bookie automata. But there are only a couple conditions on the specification logic that I'll get to in a moment. And obviously instantiation of different kinds of oracles and so forth. The goal, as I mentioned, was sort of this compositional thing and not to require it be in CPS. There are also some things that we notice here that were kind of interesting things about that we could apply to first order interprocedural programs. So I'll go through a little bit of the formal details without going too deep into them. So here's what the language that we used, which just has a number of recursive functions. And there's an alphabet of events, sigma. Here I'm again using this bold font to indicate an event. Expressions have all the sort of normal stuff that you guys are well used to. And it's including this event expression that we saw earlier. We assume...
There's no connection now between functions and events?
No.
Okay.
We assume that the program is simply typed. So there are some base types. In this case, we've worked with integers, bools, and unit. And then there are arrow types. So what we had to do is first write down the inductive big step semantics for the terminating runs. Right? These are judgments that say E will reduce to a value V, and when it does, it'll generate an event sequence varpi. And varpi is from sigma star. So these are only finite sequences, because obviously if E is going to terminate, it can only generate finite sequences. We also had to write down co-inductive big step semantics for the non-terminating runs. And these are judgments that say that E will just diverge and never return a value. However, it will generate an event sequence, pi, when pi is from sigma omega. So then once we had that, Well, I'll just show you a couple of the sort of fairly obvious ones. Obviously,
so, can I ask you something? One problem with the co-inductive semantics that I could see is that so you have co-inductive semantics where you have suppose you have the same expression appearing in two different subtrees of the co-inductive trace.
The same sub-expression?
The same sub-expression for somehow because it's duplicated by someone.
Okay.
It appears in two different steps in two different subtrees in the infinite derivation in the co-inductive semantics. In principle, it's possible to give these two traces completely different specifications, well, because it's a co-inductive relation. So, actually, is this true, or is it not true? Or maybe this is true only for expressions that are not kind of productive, they don't produce new events all the time.
So
you see what I mean? So basically, it's completely unconstrained. So how do you ensure coherence between the specifications you give to the same sub-expression if it's diverging? Is that
I see.
Maybe it's not a problem. I don't know.
I don't think it's a problem.
Okay, maybe we'll talk about it afterwards.
Okay, yeah. Let's talk about it after. Okay, so here's some examples from the inductive semantics. So the event expression obviously is going to just generate a singleton event of that name. So the function application basically says that, well, okay, if you can take E and substitute V for X and reduce it to value V prime generating event stream var pi, then that means that this lambda expression applied to V will reduce to V prime, and it'll generate a step event followed by var pi. So a step event is a special event that we require to be part of your event alphabet, going back to your question, and it ensures that it's impossible for there to be any sort of hidden computation. And this is also actually an issue that applies to the first order world. So imagine in the first order world, you're trying to prove this temporal property that eventually x is less than 0 for this program where it sets x to be 1, it does some increment x routine, and then sets x to be -1. So obviously, we would think that this property would hold, except, well, what if there's a case where this increment thing actually goes off and diverges and never actually returns? So those kinds of situations are cases where there's some hidden computation, and we didn't do a proper job of capturing the semantics of the language to make sure that we took care of it. So one thing that we can say here is that the language we've written down, we can prove that the semantics has no infinite invisible computations, which was a concern that a couple people raised earlier.
Well, you're simply typed as well.
Yes.
That would do it.
That would do it?
No, but he's got recursive functions.
Yeah, what's your typing rule for let?
Typing rule for let?
Does the E1 get to use X?
Yeah, an environment of functions because of recursive.
Can I come back to that one? So I don't have to zoom forward and back. Well, I guess I will. Oops. Let. So what was your question?
Well, didn't seem that your language allowed recursion if you're simply typed.
Oh, yes, it does allow recursion. So I'm going to come back to that.
Okay.
This is like a very slow clicker. Okay, so all right, we talked about the infinite, the hidden computation issue. Okay, and then so there's a similar application for the diverging, for the co-inductive semantics. So the type and effect system has, again, these finite and infinite specifications with the two components. In the, there's same base types, and then we use dependent refinement types, which you guys are familiar with, but the important thing is that the latent effect is that it is one of these specifications of temporal behaviors. So then in the typing rules, what we need to be able to do is perform some operations on these trace sets. So things like union. Union is not surprising. When you union these two pairs of specifications, it basically is you just distribute the union over pairing to union together the finite components separately from the infinite components. And similar for intersection. The one that comes up more here is the concatenation operation, which basically results. So if you concatenate two specifications, a finite infinite component for each one of them, you end up with a couple different cases. Well, first there's the finite component, which is only going to be the finite traces of phi1 followed by the finite traces of phi2. Then there's the infinite one. Well, there are two possibilities. Either it could diverge in the phi1 inf piece of it, or it could do some finite thing from phi1 fin followed by some infinite thing in phi2 inf. So when you sort of go down into those cases, you get the composition operator. And then subset is straightforward as well.
So are these semantic or
equations,
or is this syntax of the type system used?
So these are, we require that if you use any specification language that it be closed under these three operations. So you need to be able to say, if you, we need to be able to, for example, compute a composition. So things like bookie automata are closed under these properties.
This is semantics. This is a set of, this is trace set operations.
Yes, yes. Yeah.
And you don't have requirements about being closed under step stuttering or that sort of thing?
No, because we sort of assume this.
Otherwise, your X doesn't make a lot. The X you had in your initial example doesn't make a whole lot of sense.
No, that's a point well taken. First of all, I feel like the X operator often doesn't make a lot of sense anyway. Secondly, I mean, one, that's an interesting point to consider. Some way of like sort of hiding the step events in it. But I'm assuming for now that you've taken your specification and you've sort of carefully made sure that you've accommodated for step events occurring in them. And I realize that's like a...
So if you were to replace every event by step until event.
Yeah, for example. Yeah.
You really want to quotient over different finite sequences of steps.
Yeah. Yeah. So in order to sort of set up the oracle appropriately and prove soundness, what we had to do is write down a semantics of type and effect, which basically is this definition here. It says that an expression E is in the semantics of type tau and effect of that pair. And it's not surprising. It's basically, well, if you take the finite traces of the reduction of E, finite ones generating var pi, that var pi is going to be in fin, and then for the divergent traces pi, those pi's that are generated in the divergent ones are going to be in phi inf. So that shouldn't be too surprising. So then we can write down what's required of the oracle. Obviously, the oracle, if it tells you there's a judgment that E is going to have type tau and affect phi, then obviously that expression E has to be within the meaning of that type and effect.
Can you get the finite traces to be included in the infinite ones?
Could the finite traces be included in the infinite ones? So we found that didn't work out so well. And that the way that all of these like sort of compositions go together is by keeping them separate. And that allows us to make those composition operations where we sort of case split on all the finite infinites and so forth.
You can't show that the finite traces are included in the infinite.
You can still have some coherence constraint saying that every finite trace needs to be a prefix of some.
Yes, that's for sure. Yeah. So if you have an infinite specification, if you look at any sort of finite prefix of it, then yeah.
Oh, so an example of what actually goes wrong if you do simply combine the two. You've been saying it worked out better, and we kind of believe you, but it's hard to know why.
Well, you don't get that ability to, when you compose things together, to then keep you have to sort of approximate everything. And
an example. Illustrate the problem. So, you know, an example where you say, if you put them together, then you get the following less good result.
Yeah.
Well, maybe that would be a good thing to sort of, you know, put on a slide later.
Yeah, sure.
Because it's hard to come up with on the fly.
Yeah.
But it would be totally convincing, right? Whereas at the moment we just trust you.
Yeah. So the kind of example that I'd be looking for is something where you're reasoning about some program that does some kind of good stuff on its terminating runs, and also some kind of good stuff on its non-terminating runs that require sort of separate information. And if you sort of combine it all into one, but I'll put a slide together.
If you don't track if you're not so super keen on liveness, then there are other systems that only deal with safety properties, but also do talk about infinite behaviors where you do switch them together a bit more. So, there are other systems which work. But
something goes wrong when Eric tries it, and it's not clear to me what it is.
Yeah, I can put an example together. Right, so a couple typing rules. The Oracle one we've seen before. The combine rule is really useful. Lets you take different derivations and put them together.
On the semantics, 2 slides ago, so this doesn't. So I'm a bit confused quite where the type's working. Because if this is like a function type, what sort of this? I was expecting some kind of more logical relation-like thing. Am I just missing where?
Logical relation for?
Well, sort of the
when you get good arguments, you produce the appropriate.
Yeah. So the thing sort of that if this is an arrow type, but when I feed something in, then I will get the.
It's there in the environment. It's in the rows.
It's in the rows.
Yeah, because it's defined its function thing in terms of the open term, which is kind of strange, but works just the same.
Okay. Sorry.
No worries. Okay, so the combine rule lets you sort of take these 2 specifications and do the intersection over them. That's kind of how we came to that conclusion of getting the strong until earlier on. There's a subtyping rule, which is fairly standard, except now there's also a sub-affecting component to it. There's a const rule, which is not too surprising. There's the recursive function rule. And so something we had to be careful with in the recursive function rule is that we didn't make any unsound conclusions about what the infinite traces will be once you apply your recursive function. And so in order to solve that, we do this little erasure, this ER, which basically removes some of the conclusions about the infinite behaviors in the latent effects.
So this is no infinite traces?
Sorry?
The recursive function gives you no infinite.
You can't make, the recursive functions can have infinite traces, but you can't have specifications over them. Let me show the erasure slide. So if you have a, in the point where you have a recursive function application, we don't know whether it will actually, what its infinite behaviors will be. So we have to approximate, and this is how we chose to do it in our type system. By basically, whenever we had these latent behaviors, by inf, we basically just replace them with, okay, anything can happen to maintain soundness. But this is something that I'd like to improve.
So then do you get back something useful by using combine with an oracle?
Yes, exactly. So in our examples, it wasn't too bad for precisely that reason, that we then, in the end, use the combine rule. And if we lost information, well, we may have this termination information that we can then boil back together. That's right.
You also need some good properties of the infinite traces from the type system.
You need some good, you need some, well, you don't have too much information about, any information really about the infinite traces of the recursive function definitions from the type system. So you get that from like Oracle information that you then bring in with the combine rule.
So you have different class of programs where you could actually prove some of the good properties.
Purely within the type system, and yeah. I haven't identified what those classes are.
Well, any type system that's used for for a theorem proving system would use sigma star empty as a specification as an effect for all types, because the type system would guarantee termination.
Right, right. Yep, that's true. That's true. But then it becomes less interesting from a temporal verification point of view.
You have your data functions which you expect to terminate, like the minus operation in the example.
Right. So you do have some of that information on those functions. Yeah, that's true. Yeah, yeah. That's an example, I guess, of an oracle effectively. Yeah. Okay. So then the soundness theorem basically just again it uses the semantics of type and effect. Fairly straightforward from there. Okay. So a couple other examples. So here is an example where we had to, again, we could sort of separate out the safety and liveness. I'm just going to skip through these pretty quickly. Here's an example where we could kind of, it shows that we can have one judgment about the behavior of this rumble function and then reuse it since rumble is called again. But this is sort of standard type system stuff, shouldn't be too surprising. It's just nice to see that it works as well with the effect component. So here we need the termination oracle to show that rumble terminates, and then could reuse it. This is a more elaborate example where it has a nested temporal operator, so a G with inside an F. Here we needed a termination oracle for bar. We needed to use the dependent type system to show that bar x returns a non-positive. Actually, we needed a non-termination oracle to show that foo x does not terminate. And then the type and effect system, or type system, could show that foo x has this behavior here, where again you see the sort of step events starting to appear in the specification. And then there's another example that has some strong until operators nested inside of a G operator. And yeah, thank you. Be happy to take questions.
Questions? So the oracle thing, I mean, that takes terms, right, looks at them. It's not just expressed in terms of tricky to establish kind of inclusions between sets of languages, is that right?
Tricky to establish sets of languages?
Well, so I mean, it's like, in ordinary Hall logic or something, right, if there's a, quote, oracle for deciding internal between first order formulae or for some more sexy logic. So I might expect that this was set up in such a way that that you required you didn't give complete rules for establishing entailments between properties in your effect language, and that would be one sort of thing which would be okay. But it's like slightly more nasty if you actually ship out terms and you say, glue in a completely separate program analysis system here.
Yep, good question. So yeah, there are two pieces. There's shipping out like entailment checks between bookie automata or LTL or something like that, and then sort of shipping out questions of termination, for example.
Right, the questions of termination ought to be expressible in terms of your languages, right?
Yes.
So you should have turned it into something which doesn't have any remnant of the original syntax by the time you ship it out to something clever.
I see. No. Okay. Right. I guess I've been assuming that the termination oracle agrees on the semantics as the type system, and actually that's a requirement.
The type system should have pre-processed the question.
Right, I see what you're saying. Boiled it down to just the smallest piece of information.
You've got all those steps and things around, right? So there's a statement about steps.
Yeah, that's true.
Which ought to be nothing to do with the original.
Yeah, yeah. I can imagine some sort of rule that maybe filters that out. Yeah.
More questions?
strictly call by value, right?
Yeah, yeah.
You haven't thought about lazy evaluation at all.
Well, I think it's really interesting. Yeah, no, I think it's really. So I know some of you guys have a paper on termination of Haskell. I think it is. Maybe Demetrius and Simon.
But the point of the paper is not the termination part. It's the verification. Termination is just a tool. Well, maybe it's another example of using some. Well, no, it's an example of using liveness stuff or termination stuff to improve the precision. That's about it.
And it's also using sort of dependent or refinement types through termination.
Yeah.
So it has that in common.
Yeah, so
The specification is not temporal. I mean, there's nothing.
Yeah.
It's still above safety.
But you kind of have that termination aspect. Yeah.
You kept everything simple typed. Is that because you don't need anything more now that you have all the oracles, or it's just to keep simple?
For the examples we had, for it to be first simple type check to happen, and then to use dependent types in the type system was like, let us prove these examples. But I don't know, it might be helpful to use other type systems. We tried to at least prove the soundness irrespective of some of that stuff. But obviously some of it does appear like in the soundness proof. I mean, not the details of what the refinements are, but
recursive data types would be useful extension of practice.
Yeah, for sure, yeah. That's something interesting.
Have you considered mutating state?
No. No. Not at all.
Have you considered concurrency?
No.
Oh, weak memory.
No. Come on.
Any more questions? If not, we should thank Eric.
Thank you.